Hi, this is section 1-4, and this is what we are starting on Tuesday, October 27th. We are still looking at chapter 1, which is just labeled functions and graphs, so lots and lots to learn. And this says we're going to be building functions from functions. So here are our objectives, and you want to pull out your yellow learning objective sheet and rate yourself before the lesson. Add, subtract, multiply, and divide functions. Now, hopefully that's coming back to you. Yeah, I did that in Algebra 2. Then we have a new one here, compose and decompose functions. And you've definitely done parts of that before, so we'll be looking into that. The key here is our focus on domain, identifying the domain of the new functions when we are putting the functions together by adding, subtracting, multiplying, dividing, and composing. Decomposing, that's going to be our second day. We'll have to come back to that. And finding implicitly defined functions, that's another one we'll have to wait for the second day to talk about. But we've got a lot of things to look at over the next 2 days. And we're going to start right here. So knowing how a function is put together is an important first step when applying the tools of calculus. So how can we put functions together? And before Algebra 2, you knew about 4 operations: add, subtract, multiply, and divide. Once you got through Algebra 2, you also know that we can compose functions. So combining functions algebraically says the sum, difference, product, and quotient of functions. Let f and g be 2 functions with intersecting domains. That is huge. Because we want to keep the author's intent, when they wrote the problem, there was a reason that they chose what they did. We have to make sure that we keep track of those intersecting domains. And like it says, for all values of x in the intersection, so it has to be in both of them. The algebraic combinations of f and g are defined by the following rules. And we see the sum there that we find just by adding the 2 functions together. We see the difference that we find just by subtracting those 2. We find the product by multiplying the 2 functions together, and we find the quotient by doing the division. Now, this creates one of the situations where we have to spend more time on the domain, and that's going to be division. We have to make sure that we are not dividing by 0. So already we see again that the domain can be a little bit trickier because you have to constantly be thinking about what's taking place, and we have to remember there are 2 things we're looking for: division, not dividing by 0, and then taking an even root and making sure those even roots are being taken of 0 and positive numbers known as the non-negatives. So example 1 says we're going to define these new functions algebraically, and we have f of x equals x squared and g of x equals the square root of x plus 1. So it says find the formula for each of the following and give the domain of each. Well, that means we want to start thinking domain when we're doing these problems, but we also have to think about it every time we do some combining, every time we put functions together. Have we created a new situation where now there's division? Have we created a situation where now there's an even root? So first things first, x squared. Well, it doesn't have any division, doesn't have any even roots. Negative infinity to infinity. Then I look at g of x, and I realize, oh, yep, this one's going to be a problem. We have to make sure that x plus 1 is greater than or equal to 0, so we subtract 1 from both sides, and x is greater than or equal to negative 1. So that one will be from negative 1 to infinity. Now, if we put these together, what was important about that box was that it told us we had to look for the intersection of those 2 domains. So I start thinking about that right now and realize, well, if I'm on my number line and I'm cruising in from negative infinity to infinity, that's only going to work for f. It's not until I get to negative 1 that I find the intersection of these 2 sets. So I keep that in the back of my mind, that domain of g is going to play a large role here because that domain was restricted, and that happens a lot. All right, so we need to do f plus g, x squared plus the square root of x plus 1. And that's all we can do. we can't combine those two. They don't have the same exponents, so we cannot put those two together. And again, I want to think about the domain, and I realize, yep, the intersecting domain for these two, which we're going to use capital D again to stand for domain, and then this one was f plus g, so we'll use that as a subscript. And then we need to have the cutoff of -1 to infinity, because when we did this problem, we didn't introduce any new division, we didn't introduce any roots that weren't already there. Then we need f minus g, so that will be x squared minus the square root of x plus 1. Again, we can't combine those. That answer is what it is. It's done. And again, the intersection for the domains will be -1 to infinity. We get to f times g. Well, f times g would be x squared times the square root of x plus 1. Can't do any math with that. The best we could do would be to change our quantity of x plus 1 and make sure that we write that as the 1/2 power and go from there. But it's not really going to simplify it. It'll just change the way it looks. It will manipulate it. And again, we didn't have any new division and we didn't have any new roots that weren't already there. So the domain of f times g is -1 to infinity, because that was the intersection. Now, this is the one that we always need to slow down on, and that's going to be the division piece. We already know, yeah, division's an issue. You can't divide by 0. So we write f divided by g of x as x squared over the square root of x plus 1, and then we stop and think for a second. Wait, now it can't be -1 down there, because now I have a denominator that would have me dividing by 0. So x can't be -1. That's going to change my domain. So now I have x squared over the square root of x plus 1. And as we go through this section, that would be something we normally would not leave. You know, we would go ahead and rationalize the denominator. So we have the denominator rationalized there. And again, we can see that -1 should not be used there, because -1 plus 1 would be a 0. So what we already knew was happening with the domain is that we can't use that -1. And that was because of the division that happened in the problem. Now, the last one says we're going to do g times g. So that is the square root of x plus 1 times the square root of x plus 1, which of course would be the square root of x plus 1 squared, and then we'd have inverses, square root and squaring of each other, and we get to x plus 1. And again, that last piece right there is a little dangerous, because what we're saying is we had square roots all the way through this, and now we get to the end, and if somebody just looked at the answer, they wouldn't have any idea of the numbers that they couldn't use for the domain of this. So as we look at this, there was no new division, and there isn't any new root that happened as we went through here, but we had to use that g, which has the restricted domain. So the domain of g times g is going to be -1 to infinity. On the next page, we have a group of problems that says, you try. And this is a good opportunity for you to go ahead and hit pause and run through these and see how you're feeling about it, if you feel confident. Otherwise, I'm just going to go ahead and start teaching this like a normal part of the lesson. So we have, you try, let f of x equal 1 over x minus 3. And right away, we realize, can't use 3. That would have us dividing by 0. And then g of x is the square root of x, and that means x is going to have to be greater than or equal to 0. So we start with that domain piece again, and we say, well, this will be -infinity up to 3. Can't use 3, so jump over it on the number line, and get right back on. So with that domain again, remember we're using that union symbol to show that those two pieces are connected. They're both parts of that domain. And then for the domain of G, we have 0 to infinity. And when we talk about adding, subtracting, multiplying, and dividing, we want to think about the intersection of those two. So let's go ahead and find f plus g, and then we'll talk a little more about that intersection. So f plus g would be 1 over the quantity x minus 3 plus the square root of x. And we would just leave that exactly as it is. There's no need to try to get it to be simpler, because if we tried to get a common denominator and put it together, it actually would not be simpler to do that. So the next step would be to think about that domain of f plus g. And again, think about the number line. We're walking from negative infinity, and we get up to 0, and we have a short group there where we're going from 0 to 3 of numbers. And then we know we have to jump over 3, and we can continue on to infinity. So again, it's thinking about what is in both of these. What numbers on the number line would be in both of these? They're intersecting domain. For B, again, not a lot of math we're going to do. There it is. And just like with f plus g, we're just looking for the intersection. There was no new division, there are no new roots that showed up, and we realize, well, this is exactly the same domain that we had before for f plus g. And it is. It's exactly the same domain. Then we have to find f times g. And remember, the square root of x is like the square root of x over 1. So then we do numerator times numerator and denominator times denominator, like so. And we realize, still not using the 3. That was already part of the domain. We're using the 2 of these together. So all we have to do is keep using that intersection domain. Wasn't any new division. X minus 3 was still in the denominator. We still had our square root of x, so none of that changed. So A, B, and C all had exactly the same domain from 0 to 3, including the 0, and then from 3 to infinity. But then things change because we see division. So with f divided by g, we have 1 over x minus 3 being divided by the square root of x. And now all of a sudden we realize, uh-oh, now we can't use 0 because we just created a new denominator. X can't be 0. What we have to do is think about, for each and every step, have we divided by something we hadn't previously divided by? Did we create an even root that wasn't there before? So now what I need to do is take my 1 over x minus 3 and multiply that by the reciprocal, because we don't divide fractions, we multiply by the reciprocal, and it will be 1 over the square root of x times the quantity x minus 3. Now, we're going to leave that. I know there's a radical in the denominator there, but again, the book at this point says, hey, let's leave some of this and just focus on that domain. So at this point, we see, yeah, the new issue here is going to be we have a square root of x in the denominator, so now we can't use 0. So that did change the domain from the 3 that we were just using. That's going to mean that now we have to use our open brackets, which are our parentheses from 0 to 3 and 3 to infinity. So we're just leaving off that 0. That was going to be the problem on that one. Now, E says, let's reverse this. Let's take G and let's divide that by F. So I stopped to think about domain, and I realized, well, I'd have to leave 3 out, which is already out anyway. So nothing so far. Square root of x over 1 times the reciprocal. And that will give me the square root of x times the quantity x minus 3. And so with this one, I see, well, 0's back in. I mean, I didn't have anything here that would put that square root of x in the denominator at any point. So I can go back to the domain that I had for a, b, and c. And there it is. Now, the focus of these problems is on domain. So that's why the book is sometimes you're going to see them, rationalize the denominator like they should, and sometimes they won't. And that's because the whole focus is, can you see what new pieces we have in the domain that need to be dealt with? By the time we get to the end of this section, by the end of this chapter, and take a test on it, we should be rationalizing those. So they're kind of teaching us this in chunks, where they're saying, all right, let's just do a starter package first. Let's not focus so much on rationalizing the denominator. Let's let everybody figure out domain before we move on from there. And this last one, as we talked to Mrs. LaRue about calculus for next year, one of the things that she wants us to make sure that you realize is there are portions to the test when you take the AP Calc exam that are multiple choice. And so you may get the answer, the square root of x times the quantity x minus 3. You might also see that as x square roots of x minus 3 square roots of x, which makes sense because you would be distributing. But you also need to know that they might change this into rational exponents. And so having x times x to the 1/2 would become x to the 3/2, because 1 is 2/2, and 2/2 plus 1/2 is 3/2, minus 3x to the 1/2. So when you get to calculus for the multiple choice portion, sometimes you get done with your math and you think, well, I did everything right. Where's my answer here? And you realize that they've manipulated it and written it in a different form. So all of those are equivalent to each other. All of them are. We just need to know that they're equivalent and know how to get the math behind it to do it. Now, the next piece of this says, let's switch to another part of our objective, which is going to be composition of functions. And last year in Algebra 2, you learned that composition of functions is just really, it's a fancy way of saying substitution. That's what composition is. Let f and g be two functions such that the domain of f intersects the range of g. The composition f of g, denoted by, and we have a little box here that doesn't want to move today, f, and then it looks like a little donut hole. It could be thought of just like the little degree symbol when you say degrees Celsius or degrees Fahrenheit. So denoted f of g is defined by the rule, and then we see it with a little donut hole. But there is another way to write composition which is much more intuitive mathematically, and that is to write it with parentheses. This says f of g of x. So does this. Now, why would I say that that's more intuitive? Because in math, one of the major rules that we have about grouping symbols is that you always start with the innermost parentheses and work your way outward. And that's why this is more intuitive to think of domain. Because we realize, hey, my input is g of x, and domain is the input. So if I'm putting g of x into f, really the only thing I need to consider to start with is the domain of g. It is the input. So like it says, the domain of f of g consists of all x values in the domain of g that map the g of x values in the domain of f. So down below here we have a little diagram. The composition g of f, denoted by g, and then again, little donut hole of f, is defined similarly. In most cases, g of f and f of g are different functions. Composition is is not commutative. You know, you can't just say f of g equals g of f. Sometimes it does. Those are special, but it does not always happen that way. So we need to know that. And what they're trying to show us here is that g of x will go into f of x. And what that does is it determines the domain for that composition. So we're taking x, putting it into g, then g goes into f, and together we have the composition. So it's showing you this process of thinking about the domain. So x must be in the domain of g because g is the input, and then g of x must be in the domain of f. So it's all about the inputs, and the main input is going to be whatever is inside the deepest set of parentheses that we have there, the innermost parentheses. So like it says, in the composition f of g, the function g is applied first, then f, and that's the reverse of the order in which we read the symbols. This says f of g, but really we're going to start with g because g has to go inside the other function. It has to be substituted into it. So example 2 has us using the composing of functions. Let f of x equal e to the x, and just remember that e is just a number. Don't let that faze you at all. Try to keep in mind what that graph looks like, and you'll realize, oh, the domain of that is all real numbers. You know, it's just a growth, exponential growth function is all it is. And g of x equals the square root of x. Find f of g of x and g of f of x, and verify numerically that the functions f of g and g of f are not the same. So we start at the beginning, and we think about the domain of f, and for the domain of f, because it's e to the x, and we can use whatever x's we want to and raise e to those, that's going to be negative infinity to infinity. The domain of g, we already saw that one earlier. We know that x has to be greater than or equal to 0, so we use our square brackets at 0 and go to the right, infinity, forever. So now we want to find those compositions, and we want to think about the steps that we're taking as we do that to see if there are any new restrictions on the domain as we go forward. So the first one they want us to do is f of g of x. Now, the first thing we want to do is change that into those multiple parenthesis pieces, because what that does is that helps you realize that g of x is definitely the one that goes into f of x. So that means square root of x has to go right there for x. And that's all we can do. E to the square root of x. So now we think about the domain and we realize, oh, you got that square root piece going on in there, and g was the input, so yeah, the domain of g is now going to be the domain of f of g of x. And so we write our 0 to infinity. Again, input here is, like they mentioned, the second letter that we see with that notation of the little degree symbol there. Or when you're doing the innermost parentheses, like I said, I think it's more instinctive. So a good idea to write that in those innermost parentheses and go that way. So there we have f of g. Now we need g of f. So there we have our multiple parentheses, and we see, yep, now this time f has to go into g. So I think about what the domain of f was, and that was from negative infinity to infinity. So unless, as we're doing the math here, some new division pops up, or we have some kind of new root that happens, then we should just be able to put the domain of f. But watch as you go through and make sure. So now, this time, we will take f and put it into g. Because f was the input, our domain is going to be from negative infinity to infinity. And sometimes this makes students a little nervous because they're looking at that and saying, well, is the square root of e to the x, is that ever going to come out to be negative? And again, use the graph to remind you of the fact that it's not going to happen. So negative infinity to infinity, the input was f of x, that was f of x's domain, and that's what we use. Now, they said we had to verify here numerically that the functions f of g and g of f are not the same. So with this one, we could just pick a number and put it in for x, and then put it into the calculator and make sure that these are not going to come out to be the same. So there are special numbers that when you're trying to show situations like this, you should stay away from because they have special properties, and that would be 0, 1, and 2. So the smallest number I feel like we could get away with here would be the third for those exponents. And then we'd go ahead and punch those into the calculator and see that those are not the same. So I'm going to pause this and I'm going to put them into the calculator here, and then we'll take a look at those numbers. On the calculator, we can definitely see that e to the square root of 3 and the square root of e to the third are not the same thing. And I'm going to remind everybody that if you hit second and the ln button, which is just to the left of the 4, that's how you can get e to a power, and then you can change the exponent on that. So last thing we would want to do is, by verifying, we just showed that those two are not equal to each other, and that's what they asked us to do. So that was a part of this, and to have the problem totally complete, that has to be there. All right, so now we have another example where we are finding the domain of a composition, and again, that needs to be our first thought and our thought as we work through the problem. Have we changed the domain at all with the math that we've done? So the domain of f, and it's x squared minus 1, we can use anything in the squaring function, anything. And there's our squaring function minus 1, which means it was translated 1 unit down. And the domain of g, which we've seen for multiples today, would be from 0 to infinity because it's the square root of x. Now, we have g of f of x. So I write that in terms of my multiple set of parentheses here, so that I can see that f needs to go into g. So this needs to go here. And then I have to determine if there's any math that I could do there. And there isn't. So the next thing we do is we think about which one of these was responsible for the domain, and that was f. So we would normally want to just put negative infinity to infinity. But when we wrote this problem out, we changed what was underneath the square root, and that's an even root. So what I have to do is think, when is this going to be non-negative? So 0 or positive. And so I'd have to add 1 to both sides. And then we experience something we did earlier this year, and that would be, because x squared is always meant to be positive, we're going to have to use an absolute value for this one. And so with absolute value and greater than, that means we should have an or statement. So either x is less than or equal to negative 1, or x is greater than or equal to positive 1. And so this did change our domain. So the domain of, well, actually, I'm not going to be able to fit it right there. The domain of g of f of x is going to be from negative infinity to negative 1, including negative 1, or 1 to infinity. And that, again, was because we were taking a square root, which is an even root, and we have to make sure that that remains non-negative. Now, you see something like this, and you think, wow, that's really goofy. What does that graph look like? You know, if it's only using the numbers that are to the left of negative 1, including negative 1, and to the right of 1, and including 1, well, I'm going to pause this and graph it, and we'll get a quick square root of x squared minus 1, zoom 6, and there it is. It is really crazy, some of the things that we can come up with using math. I just love that we can represent any visual that we see with some kind of equation in mathematics. I mean, that's fantastic. So we can see, yes, you know, -1 and 1 are the cutoff, and we could go into the table, and we would see that error in that region in the middle right there. You can't use that for the domain. So we just verified this graphically. And like it says down here, we'll put a little sketch of what we saw to support our work and show people that yes, we actually did do the support graphically on this problem. Now let's look at the other one. The other one says f of g. So my innermost parentheses are g of x, which means I have to take g of x and put it in for x in the other function. And then we realize, well, that's going to create x because we have inverses there. Now this move, we would call this slightly dangerous, because here's the problem. If somebody were to see just our answer, x minus 1, they would have absolutely no idea that there are numbers that they can't use here. So that's the reason that we spend so much time talking about domain. Because we realize g went into the other function, so that is the input. And g did have restrictions, 0 to infinity. So again, we're trying to keep the author's intent. From the beginning of the problem to the end, the domain needs to remain the same. Or we are not talking about two functions that would do exactly the same thing. So now we want to take a look at this one graphically and make sure that things are going to work out. But we can't put in x minus 1 because that's not going to show us those domain restrictions. We're going to have to put in the step above. So I'll pause this and get that punched in. So now I have the square root of x, that whole quantity squared, minus 1. And when we hit graph, we can see, yep, 0 right there. That's where this is starting, and then it's going off into the right forever. So that domain was correct. And again, we want to show that we did the graphing support. To take a peek at that domain. So this is another one where, you know, if you have time when you're working on domain on the test, you probably do want to put it in the graphing calculator and just make a quick check that your domain is what it should be. And this one says you try. Again, if you want to give it a try, if you're feeling pretty confident, then go ahead, pause the video, figure it out, and then you can just fast forward and see what the answers would be. Otherwise, I'm just going to keep teaching this like normal. All right, so f of g. The first thing I do is go back up, and we actually had used exactly these same functions earlier, so we don't have to put too much thought into this. We can't use 3. Give myself a little more room to write that in. And there's the good old g that we've seen several times where we know x has to be greater than or equal to 0. So in interval notation, that'll be from 0 to infinity. We're going to take the square root of x, which is g of x, and we're going to put it into f of x. So that will give us 1 over the square root of x minus 3. Now, as you do that, you should be thinking, ooh, I just put something new in the denominator. That square root wasn't in there when I look at f of x. So that's going to create problems. And that's why at some point we say, you know what, we are going to rationalize the denominator, and we need to learn to do that. It was nice that they gave us some baby steps, but you're going to see in a second why we want to rationalize the denominator because it's going to make that process of looking at the domain a little bit easier. So we use the conjugate, and our numerator is the square root of x plus 3, and our denominator, the square root of x times the square root of x, will be x. And then outside times outside and inside times inside will cancel out because this is that sum and difference pattern. And we get x minus 9. And we realize, well, 9, that's the problem. All along, we should have seen that. And yes, we could have, if we looked up here, realized, oh yeah, the square root of 9 will be 3, and 3 minus 3 will be 0. But the big deal for this is now we have added a new restriction to the domain. So the input in this one, which was g, is from 0 to infinity, but we just found out that we can't use 9. So we have to let people know that. Now it would be 0 to 9. Jump off the number line, jump back on the other side of 9, and then continue on to infinity. G of f. F is going to go into G this time. So this will be the square root of 1 over x minus 3. Well, that's the square root of 1 over the square root of x minus 3, so that'll be 1 over the square root of x minus 3. And again, I realize I've got a new square root down there, so something's happening with the denominator. And I'm going to go ahead and rationalize the denominator and multiply by the square root of x minus 3, because this time everything is underneath that radical. And that will give me the square root of x minus 3 over x minus 3. So now it's time to think about our domain. Two pieces to what we're going to look at for the domain. And that would be the denominator. And we realize that we can't use 3. But then in the numerator, we have a radical. And that's a square root. And we know that that's going to have to be greater than or equal to 0, so it's non-negative. So we add 3 to both sides. And we realize that x has to be greater than or equal to 3. So that means the left portion of the domain that we had for f, which was the input on this one, is not usable anymore. We can't use those numbers. Now we know that it has to be greater than or equal to 3, but we also know we can't use 3 from the original domain of f. So that means when we put that all together, that our new domain will be from 3, not including 3, to infinity. All right, now we've got two really interesting problems down here. F of f. So obviously, f is the input on this one. And so this would be taking that 1 over x minus 3 and putting 1 over x minus 3 inside itself. So again, this is the little piece that would have been the x. And then we can go ahead and use our new method that we learned this year for helping us to simplify complex fractions. That has to do with finding the LCD of all 3 of the terms that we see up here. And that's obviously x minus 3. So we're going to multiply all 3 of these terms by x minus 3 to see what comes out. So 1 times x minus 3 is going to be x minus 3. Here the x minus 3's would cancel and we'll get a 1. And then we could go ahead and do the multiplication down here, the distributing, negative 3x plus 9. Then we would go ahead and combine like terms in our denominator. So now, as we go through this one, we definitely made some changes to the denominator as we went through. So, first time through, 3 was a problem. Well, that was already an issue. So we couldn't use 3 with the original f. Now we won't use it with this as well. But now we have a new restriction that comes from this denominator right here. So negative 3x plus 10, when that equals 0, that's going to be a problem. So x can't be 10 thirds in our domain. So now I have to put that together with what I already knew about the domain of f, and I'm going to run out of room, but we need the domain of f of x. So I'm on my number line, and I can go from negative infinity to 3, jump over 3, get back on the number line, and then I realize, well, I'm going to hit 10/3. Pretty quick there, 3 1/3, and then I can't use that, so I'm going to have to jump over it and continue on. So because we had so much going on with our denominators in this one, we have to constantly be thinking, how is this going to change my domain? Now g of g. So I'm thinking about the domain of g and the fact that that was from 0 to infinity. And I want to see, is that going to change if I use composition for g of g? So that's the square root of x, but we have to take the square root of itself because we're going to substitute that in for x back into g. Well, we need to take a look at this in a simplified form so we remember that square root is the 1/2 power, and that would be x to the 1/4. But since this problem came to us with radicals, that means our job is to figure out how to get it back to radicals eventually. So when a problem comes with radicals, you give your answer in radicals. When a problem comes with fraction exponents, rational exponents, you give your answer with rational exponents. So now, as I'm looking at this problem, I realize, well, I already had restrictions because this was a square root. Taking a square root of a square root just means I'm using another even root. But I'm going to be able to just use the domain that we originally had for g. There are no new restrictions. We didn't create any division as we were going through that problem. All right, that is everything from the first part of our objectives: add, subtract, multiply, and divide functions. Halfway through compose and decompose functions because we were just composing. And tomorrow we will start talking about decomposing functions.